At the previous lecture, we began to discuss the Borel functional calculus for normal operators. But the fact that the Borel functional calculus exists wasn't proved at the previous lecture. So our first goal for today will be to prove the existence theorem for the Borel functional calculus. But before we can do it, we need to make a preliminary step and to discuss useful relation between operators and sesquilinear forms. Well, first of all, let's define sesquilinear forms. Suppose that we have two vector spaces, x and y, as usual over the complex numbers. And suppose that f is a map from the product to the complex numbers. And we will say that f is a sesquilinear form in Russian полуторалинейная форма. F is a sesquilinear form if it is linear in the first argument. That is, we have the following identity. And f is antilinear in the second argument. So here we have alpha conjugate f of xy plus beta conjugate f of xz. Okay. So we are mostly interested in those sesquilinear forms which come from linear operators. So let's introduce some notation. Suppose we have two inner product spaces, H1 and H2. And suppose that T is a linear operator from H1 to H2. And we define a sesquilinear form, Ft, on the product of H1 and H2 by the following formula. It is the inner product of Tx and y. So clearly Ft is a sesquilinear form. And it is called the sesquilinear form associated to T. By the way, a nice algebraic exercise, very easy, is to show that this form uniquely determines the operator in the sense that if we have two operators, s and t, and fs equals ft, then s equals t. Okay, so in this construction, T is an arbitrary linear operator, so not necessarily bounded. The natural question is, which forms correspond to bounded operators? So let's give the following definition. Suppose that we have a sesquilinear form, F on the product of H1 and H2. Then we say that F is bounded. F is bounded if there exists a constant C, a non-negative constant C, such that for each pair of vectors x and y, x in H1, y in H2, the following inequality holds. And the smallest constant c satisfying this condition is called the norm of f. That would be inequality star. So the smallest c satisfying star is called the norm of f. We have the following simple proposition, proposition 1. First of all, a sesquilinear form f is bounded if and only if it is continuous. And second, if we take the space of all bounded sesquilinear forms on the product of H1 and H2, then the space is actually a norm space with respect to the norm defined here. The proof is pretty much the same as in the case of linear operators. So this is an exercise for you. So the proof, just recall the standard proof of the respective result for linear operators and observe that a similar proof holds in the case of sesquilinear forms. Now, proposition 2. Suppose that we have a bounded linear operators, a bounded linear operator T from H1 to H2. Then I claim that the respective form Ft is also bounded. And moreover, the norm of Ft equals the norm of T. Well, again, the proof is just a line. Actually, if you look at the definition of this form, then the Cauchy-Pirkovskii-Schwarz inequality readily implies that Ft is bounded, and that the norm of Ft is less than or equal to the norm of T. And to show that we have an exact equality, just let substitute y equals Tx here, and you get the result. It turns out that if H2 is a Hilbert space, then all bounded sesquilinear forms have this specific form. So they are associated to bounded linear operators. So we have the following theorem. Suppose that H1 is an inner product space, and H2 is a Hilbert space. Then the map from the space of bounded linear operators from H1 to H2 to the space of bounded sesquilinear forms on the product of H1 and H2. So the map which takes each operator to the respective form Ft is an isometric isomorphism. Well, okay, so we already know that this map is isometric by proposition 2. So to show that it is an isometric isomorphism, we have to show that it is surjective. So we take a bounded sesquilinear form. Let F be a bounded sesquilinear form on the product of H1 and H2. So we want to construct an operator from H1 to H2. And first of all, we do the following. We take an arbitrary element x in H1, and we define a linear functional fx on H2 by the following formula. So since we want a linear functional, I have to put the complex conjugation here. Okay, now f is bounded. And if we look at the definition of a bounded sesquilinear form, we readily conclude that fx is a bounded linear functional on H2. And moreover, the norm of this functional is less than or equal to the norm of f multiplied by the norm of x. Okay, now H2 is a Hilbert space. And we have the Risk representation theorem, which states that each bounded functional on H2 comes from a vector. So we apply the Risk representation theorem, and we conclude that there exists a unique element that's denoted by T of x because it depends on x. This is an element in H2 such that fx comes from T of x in the following sense. Or equivalently, this formula can be written as follows. F of xy, so we again put the complex conjugation here, and we see that f of xy is the inner product of T of x and y. And this holds for all x in H1 and y in H2. So this construction makes sense for each vector x in H1, and so we obtain a map. We have a map T from H1 to H2. If we now look at this formula again, we can easily observe that T is linear. So this formula holds for each x and y, and this is a little exercise, but this easily implies that T is linear. Finally, to show that T is bounded. Well, actually, at this point, we already observed that f is associated to T in the sense of our, in the sense of this definition. So T is linear, and f equals ft. And to show that T is bounded, we do the following. So T of x by the Risk representation theorem, this bijection between H2 and H2 star is isometric. So the norm of T of x equals the norm of the respective functional fx. But the norm of fx is already estimated here. And this inequality implies that T is bounded. And this completes the proof. So we already know that this map is isometric, and now we have shown that it is surjective. So it is an isometric isomorphism. So briefly, the result states that each bounded sesquilinear form comes from an operator. And we will see that this is very useful. Okay, now we are ready to prove the existence of the Borel functional calculus. Actually, we'll prove a more general result about the existence, about extending representations of algebras of continuous functions to algebras of bounded Borel functions. And at the very end of the previous lecture, we observed that such an extension theorem implies the existence of the Borel functional calculus. And here are our extension theorem, theorem 1. Suppose that X is a compact Hausdorff topological space. H is a Hilbert space. And pi is a star representation of C of X on H. Star representation. Then there exists a unique continuous star representation, pi tilde, of the algebra of bounded Borel functions on X on the same space H. And this representation is continuous with respect to the weak measure topology on B of X and the weak operator topology on the algebra of operators. There exists a unique continuous star representation, which is continuous with respect to these topologies, and which extends pi. Okay, so before we prove this result, let's briefly recall the definition of the weak measure topology and of the weak operator topology, because it is essential here. So the weak measure topology on the algebra of bounded Borel functions on X is generated by the family of seminorms, where each seminorm is indexed by a complex Radon measure on X. And this seminorm is defined as the absolute value of the integral. So this family of seminorms generates the weak measure topology. And the weak operator topology on the algebra of bounded operators on H is generated by the family of seminorms indexed by pairs of vectors U and V. And such a seminorm is defined as the absolute value of the inner product of TU and V. To prove this theorem, we need a lemma. A simple lemma from general topology. Suppose we have two locally convex star algebras. Suppose that A and B are locally convex star algebras. And suppose that phi, well, we also assume that they are unital. And suppose that phi is a continuous linear map from A to B, continuous linear operator. And suppose that there exists a dense star subalgebra, A0 in A, such that the restriction of phi to A0 is a unital star homomorphism. Well, since we work with unital algebras, we also assume that the identity of A belongs to A0. So they have the same identity. And also suppose that B is Hausdorff. Suppose that B is Hausdorff. I claim that then phi is a unital star homomorphism. Phi is a unital star homomorphism. The proof is a simple exercise in general topology. Basically, it reduces to the fact that if two continuous maps coincide on the dense subset, then they are the same everywhere. Well, not literally, because here we have to show that phi is a star homomorphism, so this involves actually some bilinear maps. But anyway, this is more or less reduced to the fact that that I've just mentioned. Okay, so let's now prove our theorem. Theorem 1. First of all, the uniqueness of pi tilde is clear because we have already proved at the previous lecture that the algebra of continuous functions is dense in the algebra of bounded Borel functions with respect to the weak measure topology. So the density of this subalgebra readily implies that if pi tilde exists, then it is unique. Uniqueness follows from the density of C of x in B of x with respect to the weak measure topology. So let's prove the existence. So first of all, we do the following. We take a pair of vectors, u and v, in H, and we define a linear functional, fuv, on this space of continuous functions, C of x, by the following formula. The Cauchy-Pirkovskii-Schwarz inequality readily implies that this functional is bounded. And its norm can be estimated as follows. This is less than or equal to the norm of pi by the norm of u by the norm of v. This follows from the Cauchy-Pirkovskii-Schwarz inequality. Let's also recall that the norm of each star representation, of each star homomorphism between C-star algebras equals 1. So this is just the norm of u multiplied by the norm of v. Okay, so this is a bounded linear functional on the space of continuous functions, and we can apply the Riesz-Markov-Kakutani theorem. And to conclude that there exists a unique Radon measure, which will be denoted by mu uv of course it depends on u and v, such that this functional is the integral with respect to mu. So we have the following equality. And this holds for each continuous function f on x. Actually, we have already used this trick when we proved the functional modal theorem for cyclic operators. Okay, so let it be Formula 1. So now, a key observation is that the right-hand side of this formula makes sense not only for continuous functions, but actually for each bounded Borel function on x. So let's use this observation. First of all, let's also, So we take an arbitrary bounded Borel function on x, and we define a map, which is actually a sesquilinear form, phi f on h cross h, to be the right-hand side of equality 1. Phi f of uv is the integral of f with respect to the same measure mu uv. So what can we say about this map? Well, it's clear from the construction of our measure that the map, which takes a pair uv to the respective measure, is sesquilinear. Because it is true if we replace mu by f, but the correspondence between mu and f is an isometric is a vector space isomorphism. So this implies that mu is linear in u and antilinear in v. So this map is sesquilinear, and after we integrate, we conclude that phi f is a sesquilinear form. Okay, let's now observe that it is bounded. So if we look at the absolute value of this, this can be estimated as the supremum norm of f by the norm of the respective measure. This is a simple property of the integral with respect to complex measure, that the absolute value of the integral is estimated in this way. Now, the norm of this measure equals the norm of f, of big F. So this can be written as follows. And the norm of big F is already estimated here. So this is less than or equal to the norm of little f times the norm of u and the norm of v. Okay, and so this shows that phi is bounded. Phi f is bounded. But we already know that each bounded sesquilinear form comes from an operator. And so we conclude that there exists a unique bounded linear operator, which will be denoted by tilde of f. Of course, it depends on f. So this is an operator on h, such that we have the following formula. So this number equals phi f of uv. And let's write once again what phi f of uv is. This is the integral of f with respect to the measure mu uv. And this formula holds for each pair u and v. U and v are vectors in H, and for each bounded Borel function f on X. And let's denote this formula by 2. This is formula 2. Now, so this construction makes sense for each bounded Borel function, and so we obtain a map. We have a map, pi tilde, from the algebra of bounded Borel functions to the algebra of operators. And formula 2 easily implies that this map is linear, because the integral is linear. Formula 2 implies that pi tilde is linear. Okay, let's now show that pi tilde is continuous with respect to the weak measure topology here and the weak operator topology here. And this is actually trivial for the following reason. So if we calculate the, if we take one of the seminorms on BOH, one of the seminorms which generate the weak operator topology, so this seminorm is indexed by a pair of vectors, and this seminorm is given here. So it's just the absolute value of this integral of this inner product, the absolute value of this inner product, or equivalently the absolute value of this integral. But the absolute value of this integral is nothing but one of the norms from this family. This is the seminorm of f corresponding to the measure f, or to the measure mu uv. And this equality readily implies that pi tilde is continuous. So this follows from this equality and from our general criterion of continuity for linear operator between locally convex spaces. So pi tilde is continuous with respect to the weak measure topology on B of X and with respect to the weak operator topology on B of H. Okay, let's compare formulas 1 and 2. After we compare these formulas, we conclude that pi tilde extends pi. Pi tilde restricted to C of X equals pi. And now to complete the proof, we use our lemma. So all the conditions of our lemma are satisfied. So pi is a star homomorphism, a unital star homomorphism on C of X, and C of X is dense in B of X. And so this implies that our lemma now implies that pi tilde is a unital star homomorphism. And this completes the proof. And as a corollary, we see that for each bounded normal operator, we can construct the Borel functional calculus. Theorem 2 about the Borel functional calculus. And this is our second form of the spectral theorem. Suppose that T is a bounded normal operator on a Hilbert space. And suppose that K is a compact subset of the complex plane containing the spectrum. Then there exists a unique Borel functional calculus for T on K. That is, there exists a unique continuous unital continuous star homomorphism from the algebra of bounded Borel functions on K to the algebra of operators, of bounded operators on H. So this homomorphism is continuous in the same sense as in Theorem 1, and it takes the coordinate, that is the inclusion map from K to the complex plane, to our operator T. And this is indeed a corollary of Theorem 1, because we can just apply Theorem 1 to the continuous functional calculus. The continuous functional calculus for the operator T. Okay. Now, our final goal in this course is to prove another version of the spectral theorem, which expresses bounded normal operators in terms of spectral measures. This will be Spectral Theorem 3. So let's start with some motivation. Suppose that H is a finite dimensional Hilbert space. And let T, well, for simplicity, we suppose that T is a self-adjoint operator on H. Of course, we know from linear algebra that T is diagonalizable. And let's observe now that the fact that this operator is diagonalizable can be written in the following form. So T is the following sum. The sum is taken over the spectrum. So the sum is finite because the spectrum is finite. Of the following operators, lambda, E, lambda, where E lambda is the orthogonal projection on the respective eigenspace. E lambda is the orthogonal projection onto the respective eigenspace, that is onto the kernel of T minus lambda. Basically, this formula is equivalent to the fact that T is diagonalizable. Okay, so this is our first motivation. The second motivation is, in fact, a more general result, which comes from the Hilbert-Schmidt theorem. Suppose now that H is an arbitrary Hilbert space, and T is a compact self-adjoint operator, on H. It's a simple exercise to show that if we apply the Hilbert-Schmidt theorem, then we get essentially the same decomposition of T, with the only difference is that now the sum is not necessarily finite, but is at most countable. So now the spectrum of the operator is at most countable because it is compact. And we have the following sum. So in the sense that this series converges to T with respect to the operator norm. So the lambdas are the same as here. So they are the orthogonal projections on the respective eigenspaces. Okay, now suppose that, again, H is a Hilbert space, and T is an arbitrary self-adjoint operator on H. And the initial question is it possible to write T in the same form as here? And a moment's reflection shows that the answer is no, because then we know that in general it can happen that T has no eigenvalues at all. So in this case, if the point spectrum is empty, it follows that the right-hand side of this formula is 0. And so the formula fails. So roughly, our goal will be to show that we can save this formula if we replace here the sum by the integral. Well, of course, here E of lambda are no longer projections onto the eigenspaces, so this is something different. And so our goal will be to give a precise meaning to this formula, to explain what it means, and to prove it. Okay, so as usual, we denote by H Hilbert space. And let's denote by PR of H the set of all orthogonal projections on H. So an orthogonal projection is a projection, an operator, which projects H onto some closed vector subspace along the orthogonal complement. We give the following definition. If we have two such projections, two orthogonal projections on H, then we say that P and Q are orthogonal to each other. And write the following symbol if their images are orthogonal. We have the following two simple results about orthogonal projections. First of all, proposition 1 gives us a useful algebraic criterion of this condition. Namely, I claim that P and Q are orthogonal even only if their product is 0, PQ is 0, or equivalently QP is 0. This is symmetric. And this happens even only if the sum of P and Q is an orthogonal projection. And in this case, if this is true, then the image of the sum, the image of P plus Q, is the orthogonal direct sum of the images of P and Q. The proof is a simple algebraic exercise for you. And proposition 2, which is also elementary, proposition 2. Suppose that we have finitely many non-zero orthogonal projections, say P1 to Pn are non-zero orthogonal projections on H. And suppose that lambda 1 to lambda n are complex numbers. Then the norm of the following linear combination, lambda I pi from 1 to n, is the following maximum, the maximum of the absolute values of lambda i's. Again, the proof is a simple application of the Pythagorean theorem. So this is an easy exercise. Okay, now we can begin explaining the ingredients of this formula. So first of all, we define a finitely additive spectral measure. So suppose that X is a set, script A is a sigma algebra of subsets of X, and suppose that E is a function from A to the set of orthogonal projections on H. And we say that E is a spectral measure, or more exactly, a finitely additive spectral measure if it satisfies the following conditions. First of all, it is finitely additive in the sense that whenever we have finitely many disjoint sets from our sigma algebra, we have the following inequality. So this is the usual finite additivity condition. Condition 2 is that E is normalized in the following sense. E of X is the identity operator. And here we also have one more condition, the so-called multiplicativity condition, which says that if you take the intersection of two sets, then the result will be the product of E of A and E of B for each pair of sets in our sigma algebra. So condition 1 is very natural. Condition 2 is also quite natural. Condition 3 looks maybe a little bit strange because it almost never holds for usual real or complex measures. But here we work with measures with values in projections. And this is a quite specific feature. And in fact, it can be shown that 3 can be deduced from 1. So the finite additivity automatically implies the multiplicativity. Well, this is not very essential for us, so I just add this condition 3 to our definition. But actually, we could prove 3 by using 1. Okay. Let's also observe that the above axioms imply that, first of all, so condition 1 implies that E of the empty set is the 0 operator. And condition 3 implies that if we have two disjoint sets, if A and B are disjoint, then E of A and E of B, the projections E of A and E of B are orthogonal to each other. Because their product is 0. Okay, let's now observe that each spectral measure generates a family of usual complex measures by the following rule. So we introduce the following notation. Suppose that E is a finitely additive spectral measure on A. So we take a pair of vectors, U and V, in our space H, and we denote by E UV the complex measure on A given by the following formula. So this is an inner product of E of A U and V. So clearly this is a finitely additive complex measure. have the following result. Proposition 3. This measure has finite variation. The variation of this measure is finite and can be estimated as follows. Well, again, the proof is quite elementary. A hint, this is an exercise, and the hint is to use proposition 2. So basically, we take x, we take an arbitrary finite partition of x into finitely many measurable pieces, and we have to estimate their sum, and the sum of their absolute values. So each absolute value for each complex number, we can write something like that, where lambda is on the unit circle. So we get a finite linear combination of orthogonal projections, and we apply proposition 2, which gives us an explicit formula for a finite linear for the norm of a finite linear combination of orthogonal projections. Okay. Let's now look at a couple of simple examples of spectral measures. Example 1. Suppose that we have a measure space, x a mu, measure space, and we define a spectral measure E on A, on H, where H is the big alto space, by the following simple formula. E of A is the multiplication operator by the characteristic function of A. So chi A is the characteristic function or the indicator of A, which is 1 on A and 0 elsewhere. So it's clear it's almost clear that this formula indeed determines a spectral measure on A. Now, example 2 is slightly more general than example 1. Example 2. Again, we start with a measure space, x a mu. H now is an arbitrary Hilbert space. And we denote by BAOX the algebra of bounded measurable functions on X. Bounded measurable, I mean A measurable. On X. Oh, no, sorry. Of course, now the measure mu is irrelevant. So we start with an arbitrary pair, x and a, where x is set and a is a sigma algebra of subsets of x. And we don't need any measure to construct this example. Okay, so we take the algebra of bounded measurable functions, and we suppose that we have a star representation, pi, of this algebra on H. A star representation. And we observe that pi generates a spectral measure by the following formula. So E of A is just the image of the respective characteristic function. This is a finitely additive spectral measure. Well, indeed, E of A is a projection because, well, chi A is idempotent, so E of A is also idempotent because pi is homomorphism. And E A is an orthogonal projection because chi A is self-adjoint. So E is also self-adjoint, and the self-adjoint projection is orthogonal. Okay, so this is an orthogonal projection, and properties 1, 2, and 3 are also easily verified. In particular, 3 follows from the fact that pi is homomorphism. It turns out that this example 2, actually describes all spectral measures. So we have the following theorem. Let it be theorem 1. So we use a new numbering because we began a new section. So suppose that, again, X is a set. Script A is a sigma algebra of subsets of X. And E is a finitely additive spectral measure on A. I claim that there exists a unique star representation, which will be denoted by EI. This is star representation of the algebra of bounded measurable functions on X. Star representation of this algebra on H, such that after we apply this representation to the characteristic function of an arbitrary set, we get E of A. And moreover, for each pair of vectors, U and V and H, if we take I E of F, this is an operator, apply it to U, and take the inner product with V, then the resulting complex number equals the integral of F with respect to the measure EUV defined there. This holds for each bounded measurable function F. And we introduce the following definition. The number E of F, this is not a number, this is an operator. Yeah? This operator is called the integral. Is the integral of F with respect to E. And it is denoted as follows. This is quite natural because, first of all, after we apply this construction, we get the usual integral of F with respect to this measure. And also, it is also natural because after we apply it to any characteristic function, we get a measure, just like in the case of the usual Lebesgue integral. The proof of theorem 1 is pretty much straightforward, maybe a little bit tedious, but it's pretty much straightforward. So I'll leave it as an exercise for you. In fact, the argument is more or less the same as in the case of the usual Lebesgue integral. Moreover, in some sense, the situation is easier here because we want to integrate only bounded measurable functions, which is much easier than to integrate unbounded function. Actually, what we have to do is the following. First of all, extend this formula by linearity to simple functions, that is, to finite linear combinations of characteristic functions, as usual, just like in the case of the usual Lebesgue integral. And then we observe that the resulting map, which is now defined on the algebra of simple functions, is a continuous star representation. This is more or less elementary. And then we just extend it by continuity, since the simple functions are dense, are uniformly dense in bounded measurable functions. We extend this map by continuity to the algebra of all bounded measurable functions. And we get our representation. So basically, the construction is the same as in the case of the usual Lebesgue integral. Okay, now in summary, we see that we have now the following one-to-one correspondence. We have a one-to-one correspondence between star representations of the algebra of bounded measurable functions and the set of all spectral measures, finitely additive spectral measures. On A. So the correspondence is given by example 2 and theorem 1. So each representation generates a spectral measure, and theorem 1 shows that this construction is bijective. Okay, now let's apply this fact to the Borel functional calculus. So the Borel functional calculus is also a star representation of the algebra of bounded Borel functions. But this representation has a special property of being continuous with respect to the weak measure topology and the weak operator topology. So now a natural question is, which spectral measures correspond to star representations satisfying this special continuity condition? Let's try to give an answer to this question. So suppose now that X is a compact Hausdorff topological space. Compact Hausdorff topological space. And as usual, our sigma algebra will be the algebra of Borel subsets. The Borel sigma algebra of X. And suppose that we have a finitely additive spectral measure on the Borel sigma algebra. We give the following definition. We say that E is regular if for each pair of vectors U and V in H, the respective complex measure defined here is a radon measure. EUV is a radon measure. That is a sigma additive regular complex Borel measure. We now have the following result, theorem 2. I claim that E is regular if and only if the respective representation, that is the integral with respect to E. So this is, we know that this is a star representation of the algebra of bounded Borel functions. So the regularity of E is equivalent to the fact that this representation is continuous for the weak measure topology and the weak operator topology. Okay, so let's prove this result. Well, the left to right implication is pretty straightforward. Suppose that E is regular. So we take a bounded Borel function f, and let's look at the following seminorm. So this is one of the seminorms on BOH, which generates the weak operator topology. So by the general continuity criterion for linear operators, we must show that the seminorm is dominated by finitely many seminorms that generate the weak measure topology. So, but what is this? This is the following, the absolute value of the following inner product by the definition of this seminorm. And we already know what is this. So we look here. This is the absolute value of this integral. But this is nothing but the seminorm of f, which corresponds to the measure EUV. So by assumption, EUV is a radon measure. And so this is one of the seminorms which generate the weak measure topology. And that's it. So this implies that E is continuous with respect to these two topologies. Okay, let's now prove the right to left implication. So we take U and V and H, and we want to show that the respective measure, EUV, is a radon measure. So what is a radon measure? Actually, this involves two conditions. First of all, we must show that this measure is sigma additive, and then we must show that it's regular in the sense that, well, it's each Borel set can be approximated from the inside by a compact set and from the outside by an open set. First of all, we prove the sigma additivity. Of EUV. So suppose that we have an increasing chain of Borel sets. And let B denote their union from 1 to infinity. It's easy to see that if you take the characteristic functions of these sets, then they converge to the characteristic function of B with respect to the weak measure topology. This readily follows from the Lebesgue-dominated convergence theorem. Okay, so by assumption, our representation, our integral is continuous with respect to these topologies. So after we apply this representation, we see that the projections E of Bn converge to the projection E of B with respect to the weak operator topology. Okay, so we, what does it mean? This means that they converge with respect to any seminorm. And in particular, this implies that EUV of Bn converges to EUV of B. But this property is equivalent to the sigma additivity of EUV. Okay, let's now show that this measure is regular. The regularity of EUV. Let's write once again the continuity property of our representation. We see that there exists a positive constant, and there exist finitely many radon measures, mu1 to mu(n) on X, such that the following estimate holds. E of f, we calculate the seminorm corresponding to U and V, and the seminorm is dominated by C by the maximum of the respective seminorms of f, the maximum from 1 to n. And this holds for each f in B of x. So basically, this is the continuity criterion for IE. Now we apply this, we substitute here the characteristic function of an arbitrary Borel set. And we get the following. This implies that EUV of B, the absolute value of EUV of B, is less than or equal to C by the maximum of mu I of B and this can be, well, I must take the absolute value here. And, well, this can be estimated just by a C mu of B, where mu is the sum of the variations of measures mu I. Now each mu I is a radon measure. The variation of a radon measure is again a radon measure, and the sum of finitely many radon measures is a radon measure. So mu is a radon measure. Mu is a radon measure, and EUV is dominated by mu. And it easily follows from the definition that if a measure is dominated by a radon measure, then it is a radon measure itself. So this implies that EUV is a radon measure. And this completes the proof. Okay. So now, as a last step, we just combine our results. Namely, we combine Theorem 1 and Theorem 2. And we get the following important result, Theorem 3, which describes representations of the algebra of continuous functions in terms of spectral measures. Suppose that X is a compact Hausdorff topological space. And suppose that pi is a star representation of the algebra C of X on a Hilbert space H. Then there exists a unique regular spectral measure E on X. As usual, I say that E is a measure on X, meaning that E is defined on the Borel sigma algebra. This is a standard abuse of language, but usually it doesn't lead to any confusion. So there is a unique regular spectral measure E on X, such that for each continuous function f on X, the following inequality holds. Phi f is just the integral of f with respect to E. And moreover, if we extend pi canonically to the algebra of bounded Borel functions, then we have the following. For each bounded Borel function f on X, pi tilde of f, this is the canonical extension of pi, is again the integral of f with respect to E. The proof is a simple combination of our earlier results. So to obtain E, we simply apply Theorem 1 to the homomorphism pi tilde. We define U of B by the following formula. And since pi tilde is continuous for the weak measure topology and the weak operator topology, we can apply Theorem 2 and see that E is a regular. E is a regular spectral measure. Now, Theorem 1 or more exactly the uniqueness part of Theorem 1, implies that pi tilde is the integral with respect to E. So we have this formula, and in particular we have the same formula for continuous functions. And the uniqueness of E follows from the bijective correspondence between pi and pi tilde. The uniqueness of E follows from the fact that that representations of C of x bijectively correspond to those representations of B of x which are continuous with respect to the weak measure topology and the weak operator topology. So this theorem gives us a correspondence between representations of C of x and the regular spectral measures. And finally, as our final result, if we apply this theorem to operators, we get our final form, our last form of the spectral theorem. Spectral theorem in terms of spectral measures. Theorem 4. This will be spectral theorem 3. Suppose that T is a normal operator on the Hilbert space H. Then there exists a unique regular spectral measure E on the spectrum of this operator such that T is equal to the integral of the spectrum of lambda dE of lambda. So we integrate with respect to this measure the usual the inclusion function of k of the spectrum into the complex plane. That is the coordinate function. Let's denote this formula by star. And moreover, for each bounded Borel function f on the spectrum, the Borel functional calculus for T is given by the integral with respect to the same spectral measure. So this is our third form of the spectral theorem, which immediately follows from Theorem 3. So again, we apply Theorem 3 to the continuous functional calculus. Okay, so this formula star, has a special name. It is usually called the spectral decomposition of our operator. Formula star is the spectral decomposition of T and the respective projections, which are in the image of the respective spectral measure, E of B, or which is the same, the characteristic function of B applied to T. So the projections E of B are called the spectral projections of the operator T. It can be shown that if we take a point here, if B is a single point, and if the respective projection is non-trivial, then this is precisely the projection on the eigenspace. But if it is 0, then this means that the respective eigenspace is trivial. So in summary, so to complete our discussion of the spectral theorem, let's draw a picture which illustrates relation between different forms of the spectral theorem. So if X is a compact subset of the complex plane, we can look at the set of all normal operators on H whose spectrum is contained in X. And we know that the set bijectively corresponds to the set of all star representations of the algebra of continuous functions. So this holds if X is a compact subset of the complex plane. This correspondence is given by the continuous functional calculus. So at the very beginning of today's lecture, we have seen that this set bijectively corresponds to the set of all star representations, of all continuous star representations of the algebra of bounded Borel functions equipped with the weak measure topology. And we equip the algebra of operators, B of H, with the weak operator topology. So we have this bijective correspondence. And finally, we have just seen that this set bijectively corresponds. So now, by the way, this bijection holds for an arbitrary compact Hausdorff topological space X, not necessarily a subset of the complex plane. And finally, we have just seen that this set corresponds bijectively to the set of all regular spectral measures. On X, on the Borel sigma algebra of X. So this picture illustrates, in summary, it illustrates a relation between these four kinds of objects. By the way, let's observe that the functional model theorem is not in this picture. And the reason is that the functional model is not canonical. It is useful and gives us many useful results about normal operators, but it is not canonical. Okay, and so this is the end of our course. If we had a little bit more time, we could also discuss another form of the spectral theorem, which describes, which gives a nice geometric picture for normal operators and describes them as operators in section spaces of measurable Hilbert bundles. And in particular, this results, so it forms the essence of the so-called multiplicity theory, and it enables us to give a complete classification of normal operators in reasonable terms. But this is outside the scope of our course. Okay, thank you.